Hello dear students, welcome back to part 4 of our teaching of our chapter Halogen Derivatives, chapter 10. Today we are going to see a very important concept of optical isomerism in halogen derivatives. Okay, this is on page number 216, subtopic that is 10.5. Now, in order to understand optical isomerism, we must understand what we mean by isomerism. So, isomerism is a phenomena in which two or more compounds, two or more molecules have the same structural, have the same molecular or chemical formula, but they differ in their structural formula. So the compounds which exhibit this phenomena are called as isomers. Okay. Now the next thing that we have to learn is stereoisomerism. Alright. Now in the higher classes, when you go for graduation level, in the FI, SY, I think so, you have isomerism in details and the types of isomerism also in details. Okay, so you have various isomerism types, stereoisomerism, optical isomerism, and so many. But what is related to optical isomerism that you have to study is stereoisomerism. Alright, the phenomena which is exhibited by some organic compounds, stereoisomerism. So remember to define stereoisomerism. How is stereoisomerism defined? So again, two or more compounds, two or more molecules, two or more isomers having same bond connectivity. Okay, having same bond connectivity or same structural formula, but differing in the arrangement of the atoms in space, but differing in their spatial arrangement. That phenomena exerted or exhibited by the isomers is called as stereoisomerism, and the compounds which exhibit are called as stereoisomers. So what is here? Bond connectivities are same, but they are differing in their spatial arrangement. Alright. Now in order, we must keep in mind that optical isomerism, which we have to study in halogen derivatives, is a type of stereoisomerism. It is a type of stereoisomerism. So in order to understand optical isomerism, we must first learn or try to grasp the important terms that we have to use when we are studying optical isomerism and then optical activity. Okay. To begin with, I will give you given you an example. Now what compound is this? CH3, CH, CH2, CH3, that means C2H5 and Cl. So this compound is an organic compound. It is an alkyl halide. Okay. It is a secondary alkyl halide. Thirdly, yes, it is a monohalogen derivative. And how do you name it? It is 2-chlorobutane. Why 2-chlorobutane? 1, 2, 3, 4. 4 carbon atoms in the longest continuous chain. 2 carbon number 2, the chloro group is attached. So this is 2-chlorobutane. Okay. Now this 2-chlorobutane has got this specific carbon, which is a special carbon atom. Why? See this carbon atom. It is attached to Cl. It is attached to CH3 on one side, attached to hydrogen on one side, and attached to C2H5 on the other. See, this is the figure. C, CH3, H, C2H5, Cl. Okay. So this is an organic compound and it is a special organic compound. Why? Because it contains one carbon atom. Same. Okay. It contains one carbon atom which is bonded to 4 different atoms or 4 different groups of atoms. So this carbon atom which is attached to 4 different groups or 4 different atoms or groups of atoms, that carbon atom is called as chiral carbon atom. How do you pronounce it? CHIRAL, chiral carbon atom. Alright, chiral. So the compound, the chiral, the whole thing is called as a chiral molecule. Okay, this is also a chiral molecule. Alright, now this compound, this chiral molecule will exhibit the phenomena of chirality. Okay, now for that we must further understand that. See, now I have drawn the structure on the board. This is 2-chlorobutane. It is containing one chiral carbon atom and so it is shown by asterisk. You imagine. Now see, it is a type of stereoisomerism. It is optical isomerism, exhibiting optical isomerism. Why? That we are seeing. So primary is that chiral, due to the presence of chiral carbon atom, it will exhibit this phenomena. Arrangement of the atoms in space is differing here. Now just see this chiral, you can say carbon atom, this chiral molecule. Okay. Consider it to be placed before a mirror. Now see, this is my right, palm or hand. This is my left hand. I place my right hand in front of the mirror. What will I observe? I will observe my mirror image. The mirror image of my hand. Correct? But if I try to pick up this and put it on the right hand, will all the points coincide? Will they coincide? No. Correct? So this chirality is going a step ahead and giving you another phenomena which is called as non-superimposable mirror images. Now see, chiral molecule, that is 2-chlorobutane, C, CH3H, C2H5, Cl. I have placed it in front of a mirror. I will observe its mirror image. But what is going to happen? This arrangement of the atoms are going to change. Correct? So there is a difference in the spatial arrangement, and therefore this gives rise to optical isomerism. Alright? Now this is well shown here. Now if I lift up this chiral molecule, 2-chlorobutane, and place it, see now, place it above this one, or take the mirror image and place it above this. Okay, what will happen now? CH3 will be CH3, but Cl will overlap over hydrogen C2H5 will be the same, but here instead of this you will get H. So see, it's shown here. Correct? This phenomena, okay, that is called as non-superimposable mirror image. Alright? Correct? So when you lift up your left hand and place it above the right, all the points do not coincide with each other, and therefore, though they are mirror images, you can say that they are non-superimposable mirror images of each other. Okay, so this kair, what is the word kair obtained from? Handedness. So right-handedness and left-handedness. Okay, so this is what you mean by non-superimposable mirror images. They do not coincide. So what does it show you ultimately? That there is a difference in the arrangement of the atoms in space. Did you get it? And why is this so? Due to the presence of the chiral carbon atom. Alright. So once we have seen what we mean by chiral carbon atom, what is chirality? So all those organic compounds which contain at least one chiral carbon atom, those compounds only exhibit the phenomena of chirality, or they exhibit the phenomena of optical isomerism. Alright? Okay. So in order to again understand optical isomerism, we will see the remaining part, that is a plain polarized light, and then what is optical activity, what are enantiomers, and so on. Okay, so I'll just be back.